Welcome to another member seminar. Today it's an honor to have Professor Jin Yang, who's an associate professor in the digital economy group, and he's going to talk about bridging the gap between AI and finance. Please,
Thank you. Thank you for the introduction. Today I'm very happy to be here to share with you my research. Actually, I'm a new member here. I joined BIMSA just last Monday. Yeah, so I'm really happy to meet you guys here. So today, first of all, I will summarize my research. Then I will provide 3 examples of finance research topics with AI. I will also cover some general machine learning topics. And last, I will conclude this talk. Okay, so first of all, let's take a look at the picture of the investment performance of some LLM, large language models, in the US stock market. You can see only one model make profit, positive profit. Right. So these LLMs are really costly to train. You may need to cost a big amount of money to train these models, but they perform really badly. Yeah, and they are inferior to that of a simple buy and hold strategy on the SP 500. Okay, so only one LLM generates profit with a low Sharpe ratio.
What does that mean, Sharpe ratio?
Sharpe ratio means the expected return divided by the risk. Yeah. So if you take a great risk, you are expected to make greater profit. Yeah. Why? Because in my opinion, because they do not truly learn finance. There's a statement from Professor Fan Xing, which says machine learning can learn finance. And also, many recent papers in the finance community conclude that some basic machine learning models outperform traditional econometric models. You can find many. Actually, I provide 2 examples here, and they applied machine learning, the basic machine learning models in international stock markets and found significant performance over performance improvement over traditional econometrics models. But why can't the most powerful AI models learn finance? Because they are approaching it in the wrong way. Yeah, and this is a table of the basic performance of the basic machine learning models across different countries. However, they are all long-short portfolios, which is popular in empirical asset pricing studies. But the long-short portfolios are often unrealistic because taking short positions in many countries is limited. All right. So generally, it's very easy to take long positions, but it's hard to take short positions. So this performance is not realistic. Right. So we say that basic machine learning models from textbooks may perform adequately, but they are not sufficient. And to be very short, what you need are carefully designed models, not the most powerful ones like LLM, not basic ones. Yeah, because in my experience, these 5 key characteristics of financial data will matter. Yeah. Okay. Let's look at these 5 characteristics. Low signal-to-noise ratio. The second one, volatility clustering, heavy tails, factor structure, and regime switching. Yeah, everyone. I think most of them cannot be learned by LLM or basic model. So can LLM or reinforcement learning, which is also very popular models, reinforcement learning, can them can they learn these characteristics without being specifically specified in the model? I think the answer is no. So these 5 characteristics, first two, the low signal to noise ratio and volatility clustering. Volatility clustering means a big volatility will followed by another big volatility. Okay, so this is a stylized facts in financial markets. And the low signal to noise ratio means the predictability of the expected value is very low. All right, so they indicate low predictability of the expected value, but high predictability of the variance. All right, and for the following 2 points, habitat and fact structure, they are also very important. If you want to make some investment, you must specify them in your model because tail risk is very important. If you do not control the tail risk, you can lose your money in one trade, all your money in one trade. Right. And the fact structure can simplify your model. That is a statistical point of view. If you consider factor structure, your model will be easy to estimate and be more accurate. Right. Okay, so these 2 points will significantly impact your investment performance. And the last one is regime switching, which is the most challenging point. And it could result in the failure of your model without any signal. Yeah.
Can you give an example of regime switching? Like what do I have in mind?
For example, financial crisis. Yeah.
Okay.
Different reasons cause different financial crisis, and that is a different period, right? For example, before 20 years, the market was quite different from now. Yeah.
What is heavy tail exactly?
Means loss, means the distribution, or tail of the distribution is heavier than Gaussian, for example. Heavier than Gaussian tail. So my research primarily focuses on the intersection of machine learning and finance. Actually, I have carefully designed some machine learning, especially deep learning models, that explicitly capture those characteristics. All right. Here I will provide 3 examples from 3 finance research topics, and I will these characteristics may correspond to some general concepts in machine learning. So I will also cover some general concepts in machine learning. Let's go to the first one, tail modeling and risk management. Well, if you are familiar with statistics, there are many distributions in statistics, right? Here, what you are going to model is the distribution of financial returns, and financial returns are return or log return. Anyone is okay. Asymmetric or skewed. It means generally they are left skewed, but for foreign exchange, things may be different. Habitat. Every financial variables are habitat. No Gaussian here. So there have been some popular distributions for modeling them, like GB2 and SGT. You don't need to know how they come. You just need to know that they are all in, as well as many special cases, right? They are all in relatively complex mathematical forms. The density functions are in complex forms, all right? You don't need to know how this density function come from. They involve beta function and gamma function, right? So because of the complex density forms, they have 2 significant shortcomings. The first one is if you want to take derivatives of the density function with respect to the parameters PQ, like lambda, they will be quite different because it involves taking a partial derivative with of the beta function or gamma function, right? That's quite unstable numerically, right? So this is first drawback. And the second one is difficult to simulate. Because of the first point, generally, these distributions are very poor practical choices for machine learning, especially for deep learning, because if you have any experience with deep learning, they are all based on large-scale gradient-based optimization, right? So you need to very easily take partial derivatives. So all these distributions are poor choice. All right, so we need to design new model to overcome this issue, right? So I found generative machine learning is a beautiful tool because it offers a different paradigm for modern distributions. It do not offer a density function, but instead it relies on a nonlinear transformation of a simple base random variable. Okay, so y here is the variable of interest, and x is a simple base random variable, for example, Gaussian. And you, through this transformation, you obtain the y, which is the target of your modeling, right? So in machine learning, especially in deep learning, people choose f theta as a neural network. For example, if you know GAN or variation autoencoder, they all choose f theta as a neural network. But we blame neural network as black box, right? We don't know what's happening in neural network. So here we design a white box f theta, which is a specific parametric function for modeling asymmetric habitable distributions. So we design this f theta. It's very simple in mathematical form, right? We design two functions, g1 and g2 here. g1 goes to infinity on the positive side, and g2 goes to negative infinity on the negative side. I will give a very simple example. This is the function graph of g1 and g2. The red one is g1, and this will result in fx looking like this, the function graph of fx. Actually, this is also the QQ plot of the random variable y against random variable x. Actually, we will propose a nonlinear transformation on the random variable. We also propose equivalently. We are proposing a QQ plot. Actually, we parameterize the QQ plot. So this will result in the CDF density and the tail set density. If you take a close look, you can find that the tail heaviness, the density goes to 0 more slowly. Yeah, so this random variable y will have a heavier tail than x. For example, if x is Gaussian, then y will have a heavier tail than Gaussian. So we obtain a new distribution, right, through this transformation. And it's quite simple in mathematical forms. Right.
Why do you call it theta? What is theta?
Theta is some parameters in G1 and G2.
Theta is the parameter in G1 and G2.
Also including mu and sigma. Yeah. So we have proved this f theta has very nice properties of tail heaviness. So theoretically, yeah, so we have some theoretical results. Besides, because of the mathematical elegance of f theta, it offers three key advantages. First, it's very easy to simulate. If you want to simulate from a density, you may have no idea how to do that. But if you are given this equation, it's very easy to sample from y because you just need to sample from x and then put it into this equation. Yeah, so it's very easy to simulate and very easy to fit to data using quantile regression because we parameterize the QQ plot. We obtain the quantile function of y very easily. So it's very easy to fit data using quantile regression, and the last one is also the most important one. It's very easy to be employed in machine learning, especially in deep learning, because it's very easy to take partial derivative of this function with respect to theta. Yeah. So we use this new distribution to predict the conditional distribution of y, where y may represent the asset return and z is the set of all predictors. So in this paper, we predict this conditional distribution for estimating risk measures such as value at risk, which is just quantile, as well as expected shortfall. Risk manager need to know these two quantities for decide to take some action or not. This is the need for risk management, right? So, okay, so this is the first point, first topic, and the second one, portfolio optimization, and generally there are two steps in portfolio construction. You need to provide a statistical or stochastic description of the multivariate stock return. And the second step is optimization. What is the objective, the constraints, and how to solve this optimization? All right, so you may know the classical Markowitz invariance portfolio optimization. So in this formulation, the description is mu and sigma, which are the parameters of the multivariate Gaussian. Right? So you need to estimate or predict them in your portfolio construction. This is a well-established field, and with a lot of papers published. And but I found that most papers focus on the second step, the optimization, but with limited attention given to the prediction. Actually, in many works, they did not predict. Instead, they use historical returns to estimate the key inputs of the optimization, such as the covariance matrix sigma, right? But in other words, they assume historical data stock returns are IID. Yeah, which is clearly wrong, right? So, but very interestingly, I found that this IID assumption remains widely adopted in hedge fund strategies, right? If we rewrite the portfolio optimization in its general form, we minimize the risk subject to some constraints. YT now denotes the multivariate stock returns. The IID assumption is equivalent to using the unconditional distribution of YT. But in our research, we use the conditional distribution. We want to predict this conditional distribution of YT. Here, YT is a multi-dimensional vector, maybe 100-dimensional, because you may select 100 stocks in your portfolio, right? And the IT minus 1 is the information set or the set of predictors. So predicting this conditional multivariate distribution is really challenging because, first of all, YT is maybe really high dimensional, right? And because there are some properties of YT habitals here and the factor structure. If we so in this work, I carefully designed a model to predict this conditional multivariate distribution by two steps. First one, statically, I designed a generative model, just like the previous one. Here, ZT is the multivariate Gaussian, and dynamically, I model the parameters of the generative model as a function of the information set. We know deep learning is popular and powerful, so someone may choose G and F, both be neural networks. But here, we let the generative model be a white box, function G be a white box. instead of a black box neural network. So this is to make the model explicitly incorporate the two properties mentioned here. Okay, but in the second step, we let the function f be a neural network, actually attention GRU. So this is the framework of our model. Once we predict this conditional multivariate distribution, we can perform the optimization. Optimization in here, and we can obtain the weights at every time t, right? Now we choose CVAR or expected shortfall as the risk measure of the portfolio, and it's better risk measure than the variance in Markovi's classical mean variance portfolio optimization. Okay, so because it incorporates the tail risk, and the resulting portfolio achieves a Sharpe ratio of about 1.5 because it's really a good performance because this is a long only portfolio. All right, no short position here. Okay, so the last topic is about financial derivatives. I will be very quick. Machine learning can help the pricing and the risk management of derivatives. You may know some classical models like geometric bounding motion used in the Black-Scholes model or the Heston model, which is more widely used in today. And also we have jump model, Levy model, many more complex models. But recently, deep learning has been integrated into the practice of the investment banks, like JP Morgan, and they use deep learning to construct the implied volatility service or do delta hedging. And we also explore deep learning in problems like risk neutral distribution extraction and risk neutral pricing, and where we observed notable advantages and improved performance. Right. So that's about financial derivatives, and because the characteristics we have mentioned corresponds to some general machine learning concepts. The first one is uncertainty quantification. Briefly, supervised learning or regression is about predicting value, right, or expected value. But uncertainty quantification in machine learning means you need to predict this conditional distribution. This is called aleatoric uncertainty. And if your model can deal with some unseen x, that's called epistemic uncertainty. Your model can know this x is not is unseen, which means your model can deal with epistemic uncertainty. Right? Uncertainty means risk in decision making. So in financial tasks, uncertainty dominates. And two reasons. The first one, signal to noise ratio is high in the tasks of video, image, texts, which means the signal dominates. But in financial world, the signal to noise ratio is surprisingly low, means the noise dominates. Right. So you can find there's no predictability of this expected value, which is directly related to your profit. Right. But high predictability of the standard deviation or the conditional variance. All right, so we have some papers, some works on this problem. Generally, not just for financial world, not just for financial data, but general approaches for predicting this conditional distribution or dealing with unseen x. Because of the time limit, I will not go into them in detail. And the second general concept is called auto-distribution generalization. This is the price curve of SP 500. A factor is in early years maybe 20 or 30 years ago, people just use head Markov models to make money from the market, right? But in recent years, head Markov models will perform badly. So deep learning can make significant profits instead. But in the future, what's the proper model? Or any model will fall? Will fail? So that's a very good question, right? Because models are becoming more and more complex, and LLM are the most powerful models we know today. It costs a great amount of money to train, but it performs badly, right? So this is because regime switching, actually. Regime switching can happen because of many reasons. For example, the financial crisis. For example, if everyone use HMM, head Markov model, the market will change too. So if regime switching happens, many models will fail. So the model that is stable across different periods is preferred. It's a challenging task, but we should also try to solve it. So regime switching is really challenging to tackle. All right, I have 3 minutes. This problem related to the concepts of OOD, auto distribution generalization in machine learning. It refers to the scenario where training data and testing data are coming from different distributions. Okay, so in machine learning tasks, in machine learning textbooks, you are told that training data and testing data are from the same distribution, right? But here, you are facing a scenario, they are different. So, but certain intrinsic properties remain unchanged. So your task is to discover those invariants. Recently, several invariant learning methods have been proposed, often coupled with neural networks. And we introduced a tree model called invariant random forest, which is an ensemble tree model to uncover intrinsic invariance within the data using decision trees. All right. So this is and this model is a general approach to OOD generalization, not only applicable not only to financial data but also to a wide range of domains. All right. Okay. So let's conclude the talk. Machine learning inference has very unique characteristics. It's very easy to apply existing models. The most powerful ones like LLM or the basic ones from textbook, but generally they do not perform well enough, or they may fail. All right. So because there's no free lunch, anyone can apply this cheap model. Cheap means you can use it without any effort. Right. You need to carefully design your own model, and at the same time, different financial problems may need different, distinct, tailored models. Yeah. So, well, I think the time is up. Yeah, time is up. So, any question is welcome.
All right, thank you. Yeah, it's really great to pay attention to finishing on time. Thank you so much. Questions?
So your advice is just buy a general index and don't worry about investing. That's the bottom line, yeah.
Buy the index. Yeah. Actually, if you can make a great amount of effort to design your own model and implement it and do for example, the risk management, you can do better than the index. Yeah. For example, the index, the SP 500 index has a Sharpe ratio of about 0.7, but you can achieve maybe a Sharpe ratio of 1. Yeah, that's impossible, but that's possible. Sorry.
More questions? So when you were designing your own model,
Yeah.
those functions that you defined for this between your Gaussian input and the desired stochastic output, how would you find the function? Do you
mean
do you discover the function?
You mean this one?
Yeah, for example.
Yeah.
No, not even here. So here, kind of, you're saying that you almost have the function, but next after this, and even after this, and even after this, maybe here, yeah, this big F.
Big
so
F,
do you discover it or do you have it?
It's existing one.
So this one is here. You use neural network.
Yeah, neural network. But the G function G is designed by us.
So what kind of functions are these?
It's G.
Yeah.
It's an extension of this transformation, which we extend it from one-dimensional to multivariate, to multidimensional, to allow the variables have tail dependence, which this one-dimensional variable is habitail, right? We mainly aim to model the habitails, but for multiple variables, we need to model the tail dependence. So we extend it to maybe 100-dimensional to allow tail dependence, some important properties in financial markets, which is not mentioned here.
Yeah. And these functions G1 and G2 are also you don't discover them, you know, right?
I designed them. Yeah.
So this is not by looking at a set of inputs and a set of outputs and asking myself what function it is that relates them. It's not like that. It's from the years of experience in financial market.
Yeah, experience. Yeah.
I see. Another question I want to ask you is, this X is many, let's say in portfolio optimization, investments, and so on. This X is many variables, like many X's. Let's say I can think of it as stock items. Am I right? For X. It's a vector, right? This X is a vector. Okay.
Here is a.
So, do you need to find correlation between components of this vector?
The correlation will be included in the transformation. Yeah. For example, you can do just a location and scale transformation to obtain Gaussian from a standard Gaussian, right? Standard Gaussian has zero correlation, but through a location and scale transformation, it will result in correlation.
Okay, I see. And then last question, which market is more volatile right now? Is it US market or is it China market?
Volatile.
In the sense of, because you have this volatility, you have this noise, right?
Yeah.
Which one is noisier?
Actually, I don't know actually.
Huh? No, but you can invest in Chinese stock or you can invest in US stock. You want to know, do I make money next month or not?
Well, I think that
for short-time portfolio.
You can do trade in the US market.
No, I'm trying to see which one makes me more money, right?
Well, I think that the problem is the relationship between the expectation and the second moment. Yeah, a market can be more volatile, but if the predictability of the expectation is high, that will be okay. Yeah.
So is the Chinese market kind of less jumping, or how is it? It's just a curious question. So it's less jumping.
Yeah.
Okay. Is it true?
Yeah, actually, Chinese market has low predictability of this expectation. Yeah. So, despite of high volatility or low volatility, is not the core reason. I think it's the predictability of the expectation.
I see. That's a good point. Yeah. More questions? Basic questions. Okay. If not, let's thank the speaker again.
Thank you all.